This video is going to be an introduction to pendulum motion, but before we do that, we're going to take a quick review of a mass on a spring as the simple case of simple harmonic motion, just as a review of what we did the first time through, because we're going to follow a very similar path when we talk about the pendulum. So we're going to start on the left side with the mass oscillating on a spring, and we have a couple expressions for the motion here. For the position, we have that the position as a function of time is equal to the amplitude times cosine of omega t, where cosine omega t represents the cosine of the angular frequency times the time. If we had a phase shift, we would have to add in a plus phi, but we're going to leave that out for right now just to simplify it. Taking the derivative, we can get the velocity as a function of time, which is omega, negative omega, times the amplitude, times the sine of omega t. Take the derivative again, and we get the acceleration as negative omega squared times the amplitude times the cosine of omega t. If we rearrange the acceleration function, we can also get that our acceleration as a function of time is equal to negative omega squared times the position as a function of time. We're going to be doing something very similar for the pendulum, but before we do that, remember that we also came up with an expression for the period of a simple harmonic oscillator. And for a mass on a spring, we found that to be that the period is equal to 2 pi times the square root of mass over the spring constant. Now, obviously, this last equation is going to change for a pendulum because we can't have a spring constant. We don't have a spring anymore. But we're going to start just by going through the derivation of this period equation again, because again, we need to follow the same exact process when we get to the pendulum. The way we came up with this was by going back to Newton's second law, and we said first that we had an acceleration of k over m times x. And to see where this comes from, just multiply the mass back to the other side. You would say that mass times acceleration is equal to Hooke's law, kx. And we just divided both sides by the mass. There should be a negative on both of those. Negative km times x. Now up here in pink we also have this other expression for the acceleration. And since we have two expressions for acceleration, we set them equal to each other. And we said that negative k over m times x is equal to negative omega squared times x. We canceled out our x's, we canceled out our negatives, and we said that omega is equal to the square root of k over m. Now we also have that our period is equal to 2 pi over omega, where omega is the angular frequency, and we just found out what omega is for a mass oscillating on a spring. So we took the square root of k over m, we plugged it in for omega, and that's how we got this expression. Okay? Again, same process for the pendulum. For the pendulum, we have two kinds of pendulums. The first one is a simple pendulum, and this is a point mass at the end of a spring. At the end of a string, I'm sorry, no springs here, at the end of a string. And the other case is a physical pendulum, and a physical pendulum is anything where we actually care about the shape. So we're going to start with the simple pendulum first, because that's the easiest one to work out. For a point mass, we know our moment of inertia is just going to be mass times the radius squared. For the physical pendulum, we have to leave moment of inertia in the equation because it's going to change each time. For either one of these, though, we can come up with similar expressions for the position, velocity, and acceleration the same way we did for the mass oscillating on a spring. For either of these pendulums, the path that they're going to follow is going to be a circular path. Okay? It's going to sweep out part of a circle. Because it's a circular path, now we need to treat this as rotational motion. So instead of regular old position, we're going to want angular position or angular displacement. That's a theta. Okay, so our First equation for the pendulum is going to be that theta as a function of time, instead of x as a function of time, theta as a function of time is equal to our angular displacement, theta max, times the cosine of omega t. Take the derivative, and we get that the angular velocity as a function of time is equal to the angular frequency times theta max times the sine of omega t, and taking the derivative of cosine, we get a negative sign that goes out in front. Now be careful here. This is angular velocity. This is angular frequency over here. Yeah, they don't cancel. They're not the same thing. They use the same symbol, but they're not the same thing. Let's take the derivative one more time to get an acceleration function. Angular acceleration, alpha as a function of time, is equal to negative omega squared times theta max times the cosine of omega t. Again, all three of these could have a phase shift. We're leaving it out to simplify at the beginning. And just like we did before, we're going to substitute our angular displacement function into the acceleration function, and we have alpha as a function of time is equal to negative omega squared times theta as a function of time. Okay, so very similar so far. Let's take a closer look at why the pendulum works and why we can consider this simple harmonic motion. Our reason for the spring being simple harmonic motion is that it has a constant restoring force, namely Hooke's law, F equals kx. For the pendulum, if we draw it out, we see that the pendulum has a restoring force provided by the force of gravity. There's this angle theta at the top of the pendulum, the angular displacement of the pendulum. There is the weight of this thing pulling the pendulum downward, so this is mg. And we can break this into components. The two components are going to be a horizontal and a vertical, and that's rotated. So we have perpendicular and parallel to the pendulum spring, or the pendulum string. The one that's perpendicular is going to be mg sine theta, and the one that's parallel is going to be mg cosine theta. The mg sine theta is responsible for the pendulum entering rotational motion. That's providing a torque. Okay, so this thing is rotating. We're at the pivot point up at the top, and the force responsible for that is mg sine theta. So the torque responsible for that rotation is this force, mg sine theta, times the length of the pendulum spring. So we could say that the net torque on this is going to be mg sine theta times the length of the pendulum. We're going to make a simplification here because this sine theta term in the torque equation is going to give us a little bit of a headache. We're going to make something called the small angle approximation, which your textbook talks about in a little bit more detail. And what that says is that for small angles, sine theta can be approximated as theta. And if you don't believe this, try it on a calculator for really small angles. So plug in 5 degrees, and the sine of the angle is going to be almost exactly equal to the angle measure in radians. And so this is true. You can test it out if you don't believe it, but this is true, which means that we can replace the sine theta with just the regular old theta. So net torque is going to equal mg theta times the length. Just like in linear, where we have an acceleration that is proportional to the position, so a equals k over m times x for linear. We're going to get a force and therefore an acceleration that's proportional to the angular displacement. So same thing. Simple harmonic motion requires acceleration proportional to the displacement, whether it's linear or angular displacement. So we need to get some kind of expression for the acceleration out of this. Remember that torque is also I times alpha. So we can replace that and say I times alpha is mg theta times the length of the pendulum. So that makes alpha mg theta times the length over the moment of inertia. So far, all of this has been for both a simple pendulum and a physical pendulum. Now is when we need to differentiate between the two, and again, we're going to do the simple pendulum first. So let's go to a new slide here. So for the simple pendulum, which again is just a point mass at the end of a string, we can ignore the mass of the string. For a point mass at the end of the string, simple pendulum, the moment of inertia is just ml squared, okay, where m is the mass of the pendulum bob. So if we substitute that into our angular acceleration equation, we're going to get that alpha is going to be equal to mg theta L over m L squared. Simplify, and we get that alpha is equal to g times theta over L. If we look back at the last slide, if we get another equation for alpha, alpha is also equal to the negative of the amplitude. No, that's not right. Alpha is equal to, let's get this out of the way. Alpha is equal to omega squared times theta. Okay, if we look back at our last slide and rewind. Just like in the linear version, linear acceleration is omega squared times linear displacement. For angular, we have alpha equals omega squared times theta. So we have two expressions for alpha. We're going to set them equal to each other. We're going to say that omega squared times theta is equal to g times theta over L. We can cancel out our thetas, and we can find that omega is equal to the square root of g over L. So what all this has been leading up to is another expression for the period of a simple pendulum. We know that t equals 2 pi over omega, so we can plug the omega that we just found in, and we can say that the period of a simple pendulum is 2 pi times the square root of the length of the pendulum over the acceleration due to gravity. Again, notice what's not in here. The mass of the pendulum bob is not in here, so you could take a really heavy pendulum, a really light one. As long as they're the same length and at the same location, they should have the exact same period. Okay, so this is our end result. That's what all of that derivation was for. This is the period for a simple pendulum. What else you need to know here? You need to know the angular displacement function. So one of the very first things we did, you need to know that theta equals theta max times the cosine of omega t. The rest of this really just derivations here. Okay? Again, this is for a simple pendulum only. If we have a physical pendulum, we can do something similar, and we can find an expression for the period of a physical pendulum. To spare you the derivation of it, the period of a physical pendulum is going to be equal to 2 pi times the square root of the moment of inertia, so moment of inertia matters now, over mgh. And h is the height of the pendulum. This expression, we've got the height of the pendulum, not the length of the pendulum. So if we had our, let's say we got a meter stick or some kind of rectangular object, we would care about the pivot point at the end. We would care about the center of mass. And h is going to be the distance, not from the pivot point to the end of the pendulum, but h is going to be the distance from the pivot point to the center of mass. Okay, so not the entire length of the pendulum. H is the distance measured along the pendulum arm between the center of mass and the pivot point, so between pink and yellow here. Okay, so that distance h, not the length of the pendulum. Okay, so that means it probably will not cancel with the distance in the moment of inertia. Okay, if you plug in for moment of inertia, you're going to want the length of the pendulum, so that would be L. Okay, so if this is a rod rotating about its end, its moment of inertia would be 1/3 ml squared, you could not cancel that with h because those are different distances. So if you have a physical pendulum, sometimes the algebra becomes a little complicated, but it remains just algebra. So let's try a sample problem that hits at both a physical pendulum and a simple pendulum. We have a meter stick swinging about a pivot point, and it's a distance h, so that's convenient for our formula. The pivot point's a distance h away from the center of mass. Okay, so our pivot point is going to be up at the top here, and our center of mass in white will be right at the center of our meter stick. So if we have a nice uniform meter stick, which we do here, the center of mass will be exactly half the length of the meter stick. This is going to swing in a nice circular path here. We'll treat it as a small enough angle to be in simple harmonic motion. And the first thing we want to know is what is the period t of this meter stick. Okay, again, this is a physical pendulum because it's not just a point mass at the end of the string. This is a physical pendulum, so we're going to need our period equation for a physical pendulum, which is going to be t equals 2 pi times the square root of the moment of inertia I over mgh. Okay, where h again is the distance between the pivot point and the center of mass. Okay, so this is h. And we know that the total length of this meter stick is, we'll just call it L. So h, if we look at the uniform meter stick, h is going to be 1/2 L. So if we start plugging in to our period equation here, t equals 2 pi, the moment of inertia of a uniform rod rotating about one end is 1/3 ml squared, and we can say mgh at the bottom, where h is 1/2 L. We can cancel out the mass. Okay, so again, we see that mass should not matter for a pendulum. Working with these fractions a little bit, we can move the 2 to the top, 3 to the bottom. We can cancel out 1L from the top and the L from the bottom. So the period of this is going to be 2 pi times the square root of 2L over 3G. I'm plugging in. We know the length is 1 meter. And then we have 3 times 9.8. Plugging in, we see that the period of this pendulum is going to be 1.64 seconds. So that's our answer to part A, 1.64 seconds. For part B, we want the length of a simple pendulum that would have the same period that we just found. So we want to use our simple pendulum formula. For a simple pendulum, we know that our period is going to be 2 pi times the square root of L over G. We want to plug in 1.64 for our period, and we want to solve for L. So we're going to do that. 1.64 equals 2 pi times the square root of L over 9.8. Again, we don't have our meter stick anymore. We have a simple pendulum. So we don't know the length. That's what we're solving for. We know everything other than the length. So it's just a matter of doing the algebra out. And that we get that L is 66.7 centimeters, or 2/3 the length of the meter stick. That's going to do it for this video. Please remember, this is not a substitute for reading your textbook. It's not a substitute for doing the example problems in your textbook. Your textbook works out some sample problems for you. Please make sure you're reading through those. If you still have questions after watching this video, after looking at any of the other resources I post up on Schoology, please send me an email. Do not leave this assignment for January 1st. Enjoy the rest of your break, guys.